Look at this pulse of light traveling through a fiber optic cable. It represents the exact moment a user hits send on a standard large language model chat interface, kicking off a massive computational sequence. Beneath that simple text box, the application initiates an HTTP POST request. An HTTP POST request is a standard Internet Protocol method used to securely package and send data to a server. This is the actual delivery mechanism, routing the user's input across the network. The body of that request is the payload, formatted as a sophisticated JSON data structure. JSON, or JavaScript Object Notation, is a standard text format for storing and transporting data. This payload is a multi-dimensional configuration space that maps everything from the model's behavioral constraints to its access to external knowledge. The request is wrapped in HTTP headers, containing essential metadata that governs the request's lifecycle. These headers include bearer tokens, security strings that authenticate the application's identity, along with organization identifiers. Providers use these specific strings to route the data correctly and apply precise billing and rate limits. Inside the payload itself, the JSON body dictates three core aspects of the model's operation. It defines the system's behavioral constraints, sets the precise boundaries of its external knowledge, and controls the stochasticity, or mathematical randomness, of its generated output. To understand how this data structure controls the AI, we must deconstruct the request and response frameworks, map the mathematical formulas that govern token sampling, and examine the recent architectural shift to stateful APIs. Mastering these granular parameters is the critical skill in modern AI engineering. It is the exact mechanism that turns a passive multi-billion parameter neural network into a highly predictable, production-ready system. A modern JSON request payload is divided into three primary clusters. The first of these handles identification parameters. This diagram shows the foundational structure of the payload, starting with the required model parameter at the top. This single string dictates the exact version of the model being invoked, establishing the absolute intelligence ceiling for the system. It defines the maximum context window capacity and the specific operational capabilities the model can support. Below the model identifier is the messages array. This list of objects creates a functional hierarchy. By assigning different roles, specifically system, user, and assistant, the payload categorizes incoming data so the model can differentiate between hard-coded instructions, current human inputs, and its own past outputs. The user role contains what is technically defined as the prompt. In a multi-turn payload, the prompt is specifically located in the final user message of the array. It acts as the immediate operational trigger, the specific question or command the model must execute at that exact moment. Everything else in the payload surrounding that prompt is the context. This acts as the model's working memory. It is the broad informational environment that informs the model's decision-making process before it begins generating an answer. This context is distributed across specific locations. Instructional context lives in the system role. It provides the behavioral constitution for the model, establishing the persistent rules, persona, and tone that govern how the final prompt must be interpreted. Conversational context is maintained in the assistant role. This contains the history of the model's previous responses, providing the threaded timeline necessary to resolve co-references and maintain logical continuity across multiple interactions. Engineers also deploy injected context through systems like Retrieval Augmented Generation, or RAG. RAG is an architecture that retrieves relevant facts from an external database and explicitly inserts those text chunks directly into the payload, grounding the model in proprietary data outside its original training set. Prompt engineering is the localized task of phrasing the right question within that final user message. Context engineering is the macro task of constructing the entire mental world, the rules, the memory, and the retrieved facts that the model operates within. Large language models do not generate text by knowing the factually correct answer. They predict the probability distribution of the next token based on the input. The behavioral constraints cluster of the payload controls this probabilistic selection process. This diagram illustrates the mathematics of token selection, featuring the temperature formula above a bar chart of logits. Logits are the raw, unnormalized scores generated by the neural network for each possible next word. The temperature parameter, represented by T, is a scaling factor applied to these raw logits before they pass through a softmax function, a mathematical operation that converts those raw scores into a final set of probabilities. When an engineer lowers the temperature to zero point 0.1, the mathematical distribution sharpens. The most likely tokens become exponentially more likely, forcing the model into a highly focused, deterministic output sequence. Conversely, increasing the temperature to 1.5 mathematically flattens the distribution. It increases the probability weight of lower-ranked tokens, introducing greater variance and creative diversity into the generated text. An alternative truncation method is top-P, or nucleus sampling. Instead of scaling the entire vocabulary, the payload instructs the model to only consider the smallest set of tokens whose cumulative probability exceeds a specific threshold, neatly cutting off the long tail of highly unlikely words. Because these models generate text autoregressively, one token at a time, they carry the engineering risk of repetition loops, where the system gets stuck predicting the exact same sequence of words continuously. This diagram displays the formula for the presence penalty parameter. By applying a negative mathematical weight to the logit of any token that has already appeared in the sequence at least once, this penalty physically forces the model to move on to new topics. The frequency penalty parameter uses a similar logic, but reduces word-level redundancy. It shrinks a token's logit proportionally to its exact usage count. The more a word appears, the harder it becomes for the model to select it again. By adjusting these specific numerical levers within the payload, engineers mathematically constrain the probabilistic behavior of a neural network, guaranteeing reliable text generation. Controlling word choice is only the baseline requirement. For an AI to safely integrate with larger software systems, the payload must force the model to output structured, machine-readable data. Early implementations relied on a basic JSON mode, which ensured syntactically valid code, but offered no guarantees regarding the exact keys and values. Modern frameworks employ structured outputs, where the developer embeds a strict, predefined JSON schema directly inside the response format object. When this strict schema is applied, the inference engine relies on constrained decoding. Constrained decoding is a process that mathematically masks out any generated tokens that would violate the specified schema, guaranteeing the model populates the exact object structure required by the downstream application. The payload can also include a tools array. This expands the operational context by defining external functions the model is permitted to execute. By including these definitions, the model gains the ability to interact with the environment through specific, predefined actions. The model evaluates the JSON schema descriptions of these tools against the user's prompt. If it determines a specific tool is necessary to answer the query, it halts its standard text generation and returns a structured request to execute that external function. However, defining every possible tool in line within the request payload introduces a severe scaling bottleneck. This practice causes massive context bloat, consuming tokens rapidly and degrading the model's accuracy as the prompt grows too large for the system to process effectively. This diagram illustrates the architectural solution, the Model Context Protocol, or MCP. Instead of cramming definitions into the local payload, MCP allows the model to bypass the bloat, routing secure connections to specialized external servers that host their own independent tools and data sources. Strict schemas and the Model Context Protocol elevate the payload. It functions as a secure, deterministic router capable of orchestrating complex agentic workflows. Once the server processes the request, the API returns the response payload. This data structure precisely mirrors the complexity of the input, providing the generated content alongside extensive metadata detailing the inference process. This visualization of a response payload shows the primary output contained within the choices array. Inside this array is the finish reason string, a critical piece of engineering metadata indicating exactly why the model stopped generating text. A stop reason means the model reached a natural conclusion. A length reason indicates the output was truncated due to a token limit constraint, requiring the system to request a continuation. A tool calls reason dictates that the system must halt text processing to execute an external function and return the results. The response also contains the usage metadata object. This serves as the fundamental ledger for resource management, providing a precise, auditable count of the tokens consumed during the entire request-response cycle. As model architectures have evolved, standard token counts have been subdivided. Advanced models now perform internal chain-of-thought processes before outputting an answer. These steps are meticulously tracked as reasoning tokens within the usage metadata. These internal reasoning tokens remain completely invisible to the end user on the chat interface, but they heavily consume computational resources and directly drive up the total token cost of the transaction. To offset these costs, providers use prompt caching mechanisms. OpenAI hashes the initial prefix of the prompt, while Anthropic allows developers to set explicit breakpoints. These mechanisms drastically slash token costs and reduce latency when the same heavy context is sent to the server repeatedly. Rigorously parsing this response metadata is the only mathematical way developers can accurately monitor cache hit rates and optimize the long-term financial efficiency of an application. The legacy chat completions architecture possesses a core structural flaw. The API is entirely stateless. The server retains zero memory of the interaction between requests. This diagram illustrates the stateless loop. Without native memory, the client retransmits the ever-growing conversation history inside the messages array on every turn. During long-running interactions, this ballooning payload destroys network latency and causes redundant token costs to explode. The solution is the Stateful Responses API. By setting a simple Boolean value of store true in the request payload, developers activate a major architectural shift in how data is handled. In this stateful model, the working memory is maintained directly on the provider's backend servers. The API stores the ongoing state of the interaction using dedicated items and conversations objects. Look at the stateful loop in this diagram. The client's payload input is no longer a massive message array. It becomes a lightweight, constant-sized pointer referencing a previous response ID, while the heavy memory block expands securely server-side. Stateful, item-based payloads allow large language models to execute autonomous, multi-turn reasoning loops without the client orchestrating every step of the process. This architecture enables the transition from simple text generation to fully agentic behavior.